Dual nature of radiation was postulated by. Correct option is option B, de Broglie. J. Thomson discovered electron. Max Planck is known for his quantum theory. And Einstein is known for his theory of relativity. And also he got Nobel Prize for photoelectric effect. So for this question, dual nature of radiation postulated by de Broglie. Dual nature means radiation both acts as matter and wave. The ratio of wavelengths associated with a proton and an alpha particle of same kinetic energy in the same order is. We know that equation for wavelength lambda equal to 1 by square root of 2me, where E is the kinetic energy. Or we can write lambda proportional to 1 by square root of mass. Using this equation, we can write lambda of proton, that is 1 by square root of mass of proton. Lambda of alpha, 1 by square root of mass of alpha. So lambda of P divided by lambda of alpha, you will get, that is, you can take the ratios of these two equations. Is 1 by square root of mass of proton divided by 1 by square root of mass of alpha. That is 1 by square root of mass of proton into, when these terms goes to the numerator, we can write square root of m alpha divided by 1, or square root of m alpha divided by mp. And we can consider alpha particle as helium nucleus, that is He24, where 2 represent atomic number of protons, and this 4 represents mass number, that is total number of protons plus neutrons. So here mass is 4. So we can write square root of 4 divided by, and again proton we can write it as hydrogen 1. Here the upper number that represents mass number. So here also we can take mass of proton as 1. So you will get square root of 4 by 1 or 2. So the correct option is option B, 2:1. The threshold wavelength for photoelectric effect of a metal is 6000 angstrom. Work function of the metal is approximately. Equation for work function is W, or phi you can write, that is Hc by lambda, that is equal to, H is Planck's constant and its value is 6.62 into 10 raised to minus 34, and c is velocity of light, that is 3 into 10 raised to 8. You will get in joule divided by lambda. Since the answers are in electron volt, all are in electron volt, what we can do is convert this joule into electron volt. How we can convert? 1 joule is 6.24 into 10 raised to 18 electron volt. So when you multiply this with 6.24 into 10 raised to 18, you will get in electron volt. So when you calculate this, you will get 12398 into 10 raised to minus 10 divided by lambda. Or approximately you can write 12,400 into 10 raised to minus 10 divided by lambda in electron volt. So you can remember this equation and directly put the value of lambda here. That is 12400 into 10 raised to minus 10 divided by lambda is 6000 into 10 raised to minus 10 since it is in angstrom. So you will get 2.1 electron volt. Option B is the correct one. Photon of energy 2 electron volt fall on a metal surface of work function 1.1 electron volt. The stopping potential is equation for kinetic energy is energy h nu minus work function W. We know that stopping potential means the negative potential applied to the anode to stop photoelectrons. Here h nu is 2 electron volt minus work function is 1.1 electron volt. So you will get 0.9 electron volt. We also know that energy we can write charge into potential. So potential we can write energy divided by charge. Here we have to find the potential. So it is energy 0.9 electron volt divided by charge. That is that of electron. So you will get 0.9 volt. So correct option is option B, 0.9 volt. When photon of energy h nu fall on a metal plate of work function phi, the maximum kinetic energy of photoelectron ejected is E. If the frequency of radiation is doubled, then maximum kinetic energy of photoelectron is. We know the equation h nu equal to phi plus E, where h nu is the photon energy, phi is the work function. That means minimum energy needed to eject a electron from the metal. E is the kinetic energy, maximum kinetic energy of the electron. So, when the frequency of radiation is doubled, that is nu becomes 2 nu. So, this equation becomes h into 2 nu or 2h nu equal to 5 plus E dash. That means when frequency varies, kinetic energy of the electron also varies. So, you will get two equation or 2 minus 1 gives 2h nu minus h nu, that is h nu only. 5 and 5 will get cancelled. E dash minus E, or E dash is equal to E plus h nu, that is E plus h nu. We know that E plus phi. So 2E plus phi, that is E dash is equal to 2E plus phi, that is this is getting added plus phi. That means this one gets added up to 2E. So the maximum kinetic energy will be more than double. That is 2E plus phi means more than double. Option B is the correct one. The momentum of a photon of wavelength lambda or frequency nu in SI unit is equal to. We have to find out the momentum. Equation for momentum is h by lambda, that is h by, we know that c equal to nu lambda, so lambda is c by nu. Let us substitute this one here. So h by lambda is c divided by nu. Nu will go to the numerator. So you will get momentum h nu by c. Option A is the correct one. Electron emitted during photoelectric effect has stopping potential V0 volt. When the photoelectrons are further accelerated through a potential of V volt, then the minimum wavelength associated with the electron is. We have to find out lambda here. We know the equation for energy is, that is charge into potential. Here the initial potential is V0. So we can write UV0. Or since charge is electron, we can write EV0. So we can write energy is equal to EV0. Energy means kinetic energy. So this is the initial kinetic energy. So when the photoelectrons are further accelerated through a potential of V volt, final kinetic energy becomes changes to E into V0 plus V. We also know that equation for lambda is h by p, where p is the momentum, that is h by p is square root of 2me. So we can substitute the value h by square root of 2m. This one we already know. So we can substitute here. So we will get 2m into E into V0 plus V. So in this one, h by 2m into V0 plus V, option A is the correct one. Work function of an electron is 3 electron volt. The maximum wavelength of light which can produce photoelectric emission is nearly. We have the equation for work function phi equal to hc by lambda. We can find out lambda as hc divided by phi. When we calculate hc in electron volt, we can write the equation as lambda in angstrom is equal to 12,400 electron volt divided by phi. So it is 12,400 divided by phi is 3 electron volt. So when you calculate this, you will get approximately 4120. We already said that it is in angstrom. So in angstrom. So option A is the correct one. For this, you have to learn this basic equation. So option A is the correct one. If Ra 88-26 nucleus undergoes 8 beta alpha decays and 6 beta decays, the resulting nucleus is XZA, where Z and A are respectively. We have to find out the value of Z and A. It is given that Ra 88-26 undergoes 8 alpha decay. Alpha is He24, helium-24 nuclei, and 6 beta. 6 beta is, we can write beta -10 plus resulting nucleus, it is given that XZA. So here 88 is the total one. Let us find out on the right hand side. That is, this is 8 times. So 8 into 2 is 16. So we can write here total 16 comes, and 8 into 4, 32, plus here also 6 times. So 6 into -1 minus 6, 6 into 0, 0 plus XZA. Z is the atomic number, A is the mass number. So when we compare here 16 minus 6, that is 10. So here Z should be 78, so that 78 plus 10 will become 88. So the equation will get balanced. So we will get X Z as 78, and here total is 32 plus 0, that is 32 only. Here it should be 226. So here A should be 194 plus 32 gives 226. So it will be 194. So 78, 194, option D is the correct one. The second line of Balmer series of hydrogen atom has wavelength 4861 angstrom. The wavelength of first line is nearly. See, this Lyman-Balmer-Paschen bracket P-Fund series are electronic transition in hydrogen atom. So, when the electrons excited to 2, 3, 4, 5, 6 states comes back to the ground state, that is n equal to 1 state, you will get Lyman series. So when the electrons comes to n equal to 2 state, you will get Balmer series. When it comes to n equal to 3 state, you will get Paschen. When it comes to n equal to 4, you will get Bracket. When it comes to n equal to 5, you will get P-Fund series. So we are talking about Balmer series. So it comes to n equal to 2 state. So second line of Balmer series means this green line from where it starts n equal to 4. So it's coming from second line coming from n equal to 4 to 2. Let us write the equation for wavelength 1 by lambda r equal r into 1 by n1 square minus 1 by n2 square, that is r into 1 by n1 is 2, n2 is 4. Here it is given. So you will get 3r by 16. Similarly, for the first line we have to find out for the first line. So 1 by lambda r into 1 by, for the first line from where it is coming from 3, from n equal to 3. So first line comes to coming from n equal to 3 to 2. So 1 by 2 square minus 1 by 3 square, that is 5r by 36. Let it be lambda 1, let it be lambda 2. So from this you can find out R value. R value is 16 divided by 3 into 1 by lambda 1, that is 1 by 4861. So you can substitute this value in this. So you will get lambda 2. Lambda 2 is 36 by 5r, or 36 by 5 into r value is 16 divided by 3. 3 will go to the numerator and 4861. Just substitute the values so that you will get, it's nearly 6563 angstrom. So option D is the correct one. And we can also say that this Lyman series that you can see in UV, and this Balmer series in visible spectrum, Paschen in infrared region, Bracket also in infrared, and P-Fund. So option D is the correct one.